Welcome back to Applied Algebra and Trigonometry. Today we're going to apply all of those formulas that we've learned to solving trigonometric equations, meaning we're going to combine those trigonometric identities and values and ratios with algebra to solve equations. Example 1. An equation containing a trigonometric function to which we can apply algebra. So we're solving for the angle. That's the only variable there. So we're going to do it just like we do in algebra. We're going to isolate the variable. We're going to do that by doing the opposite of what is written here. The 1 is added there. We're going to subtract the 1. Same thing you've been doing for years with algebra. Okay, now we have 2 times the cosine of theta. Therefore, we're going to do the opposite, going to divide by 2. So the cosine of theta equals negative 1/2. Okay, let's think about that. I began talking about this during our last class session, I believe, the last video. When you have a Cartesian coordinate system, let's do it in radians to become more familiar with them. Okay, there are the angle measures of the axes, measured in a counterclockwise direction from the positive x-axis. And I told you that all students take calculus. See you there someday. All right, that tells us the ASTC which trigonometric functions, or ratios rather, are positive in those quadrants. Therefore, the only place that cosine is negative are in quadrant 2 and quadrant 3. So we can draw our reference triangle. In quadrant 3 it will look like that. In quadrant 2 it will look like that. And we're talking about cosine. Cosine is the adjacent over the hypotenuse. The hypotenuse is always positive. So we know this is going to be 2. And the adjacent side is 1. In either of these quadrants, it is a negative 1. So we have 1, 2, what's the other side? Special triangle, square root of 3. Let me redraw one of those special triangles a little more to scale because I want this side to be noticeably shorter than the other. Okay, I'm redrawing the one that's in the second quadrant. This is a 30, 60, 90 triangle. The 30-degree angle is always opposite the smaller side, and the 60-degree is opposite the larger side. But wait a minute, we were going to do this in radians, not in degrees. Well, pi divided by 6 radians is equal to 30 degrees, and pi divided by 3 is equal to 60 degrees. And you can check out those quick notes on how you could calculate that. So let's expand our picture a little bit so we can actually write in there what we need to. Let's zoom in further. All right, and we need the standard angle, not just the reference angle that we already have. But what is this angle? We don't make it all the way to pi. In fact, we are pi over 3 short from that. So what we have actually is 2 pi over 3. When you're checking my work there, remember to find a common denominator before you subtract the pi over 3. All right, the other angle, though, is not less than 180. In fact, it's pi over 3 more than 180. So that angle is pi plus pi over 3, or 4 pi over 3. And either one of those angles satisfies this equation. That means we have 2 solutions. You can plug your answers into the original equation to check them. I recommend you do that with your calculator. When solving trig equations, you may get 2 answers, you may get 4 answers, you may get 8 answers. Just keep working till you've found them all. Let's do another example. Example 2. Okay, for this one, a little more complicated with the initial equation. 4 times the tangent of x plus 2 equals 3 times 1 plus the tangent of x. Okay, take a moment, pause the video if you need to, see if you can figure out where to start. I'm solving for x, so I need to get all of the x's on one side. This 3 is kind of in the way where it is now. I'm going to distribute it. Now remember, there may be, and probably are, different ways to do this. This is the one I'm choosing. Okay, I distribute that 3. Now, tangent is in 2 different terms on different sides of the equal sign, so I'm going to move this one to the other side by subtracting it from both sides. So that's going to give me just the tangent of x on the left-hand side, plus 2 equals 3, and plus 0. I won't bother to write that. Now I'm going to subtract the 2 from both sides as I continue to isolate my x. Tangent of x equals 1. Where does the tangent equal 1? The tangent of any angle is equal to the opposite over the adjacent. And if the opposite over the adjacent is going to equal 1, then these two have to be the same. Whatever they are, I don't know, b, it has to be the same. The only triangle that gives us equal sides for a right triangle is this special triangle. And each of these angles are the same. They are pi over 4. Remember, I told you we were going to practice radians. Pi over 4 is equal to 45 degrees. But this is a positive tangent case. All students take calculus. So the ratio is positive. That does not mean all the sides are positive. We have a 45 right triangle here, and the angle measure is pi over 4. Well, it just so happens that that reference angle in the first quadrant is equal to the standard angle. Not so in quadrant 3. In quadrant 3, our x value is negative, our y value is negative. The hypotenuse is always positive. But to express the standard angle, we have to go all the way around past 180, or past, pi, and then add to that pi over 4. So zooming in again, we get pi plus pi over 4 as the measure of this standard angle here. So that would be 5 pi over 4 as the measure of that standard angle, and the measure of the standard angle in the first quadrant is the measure of the reference angle. So let's write down our answers here. X equals pi over 4 and 5 pi over 4. Time for example 3. This one will be a little bit different. Remember all of the algebraic methods of solution that we have used. In particular, with this one, my suggestion is that you move 3 cosecant of x to the other side by subtracting it from both sides. Not because it's going to disappear or add to be 0 or anything. Well, it will add to be 0 on the right-hand side, but because it gives you something very interesting on the left-hand side. You have cosecant squared of x minus 3 cosecant of x plus 2 equals 0. Now, you can perform a substitution here that may help you see it better. If you let the cosecant of x equal, z, then this first term, cosecant squared of x, becomes z squared. Then you have minus 3 times z plus 2 equals 0. That we can factor. We can factor it into z minus 1 times z minus 2, because negative 1 times negative 2 will give us that positive 2, and you can check it out. Do the distribution if you need to assure yourself that that is true. Now that it is completely factored, we can set each factor equal to 0, because if either factor is equal to 0, when you multiply them, your result will be 0. All right, at this point, we need to add 1 to both sides of that equation to get z equals 1. If we add 2 to both sides of this equation, we get z equals 2. Ta-da! Except we're not done. We have not solved for our original variable. Our original variable is x. So everywhere I see a z, I'm going to replace it with the cosecant of x. So the cosecant of x equals 1, and the cosecant of x equals 2. Now, how can that be? Let's think about our special triangles. Just a nod to some of you who maybe didn't need to do the substitution, but could see from this second step that you could go ahead and factor it and wind up eventually where we are. But where exactly are we? As I've told you before, I'm much more comfortable with sine and cosine than with cosecant, secant, and cotangent. So let's convert cosecant to sine. Let's see, cosecant of x is equal to 1 over the sine of x, and that's equal to 1. We approach our second solution. We have 1 over the sine of x equals 2. But we haven't solved for x yet. We still need to work to isolate it. Let's take the reciprocal of both sides. The sine of x equals, the reciprocal of 1 is 1. Now, the interesting part is in the other possible answer. The reciprocal of 2 is 1/2. We have positive values for sine, so these angles must be in the first quadrant or the second quadrant. But where does sine equal 1? If it's close to the x-axis, sine is close to 0, so the sine of 0 is 0. What about here? If it's at 90 degrees, is the sine of 90 degrees 1? Yes, it is. Well, we could express this as 90 degrees, but remember we're practicing radians today. So x would be pi over 2. That's what it's equal to. It would not be going down here, because then it would be a negative 1 and we have a positive value. So we have pi over 2, but we still have to find other possible value for x. We need to draw an angle in the first quadrant so that, let me do it in white so I'm a little more consistent, in the first quadrant, so that the opposite side over the hypotenuse gives us 1 over 2. That means this next side must be square root of 3. That's what it would look like in the first quadrant. In the second quadrant, where sine is also positive, it would look like this, kind of. So we have a positive 1 over a positive 2. Okay, that's good. And just to mention it, the x value here would be the negative square root of 3. Our smaller angle in each triangle is located here. If we were doing degrees, that would be the 30-degree angle, but we're doing radians, so that angle is, in the first quadrant, pi divided by 6. What is it in the second quadrant? We need the reference angle here. So it will be pi minus pi over 6. So that will give us 5 pi over 6. So that is our final answer. We have 3 answers, actually. We have these two and that one, and you can check them all in the original equation using your calculator and the pi button. However, the conventional way to report these is to put them in order from smallest to largest. All right, that was example 3. Let's move on to an example 4. Okay, it's time to get creative. Let's see, we have 3 times cosecant squared of x. Let's divide both sides by 3 and see what happens. So this will be equal to 4/3 on the left-hand side and the cosecant squared of x on the right-hand side. I'm not going to leave that as the cosecant squared. I'm going to convert it to the reciprocal of sine squared. And I'm solving for that x that's in the sine, so I'm going to take the reciprocal of both sides. 3/4 equals the sine squared of x. And now, to finish up solving this, I need to take the square root of each side. Was that radical sign in our original equation? No. We're using it as a method of solution. So when you do that, you must consider both the positive and the negative square roots. And that would be the square root of 3/2. Positive square root of 3/2 and negative square root of 3/2. So since we must consider both negative values for the sine of x and positive values for the sine of x, solutions exist in all 4 quadrants, where sine is positive and where sine is negative. The reference triangle, which we're looking at, has a larger angle of pi/3. So in the first quadrant, our standard angle is pi/3. In the second quadrant, it's going to be pi minus pi/3, or 2pi/3. In the third quadrant, we're passing pi, so it will be pi plus pi/3, or 4pi/3. And then finally, we have to go all the way around into quadrant 4 for our final answer. And we're going all the way around, not quite to 2pi. So this last measure will be 2pi minus pi/3. Or that's equal to 5pi/3. So these are the angles, standard angles. Each of them is a solution to the equation. You can check your answers using your calculator. Just make sure it is in radians. But the way we would list these in the end is x equals pi/3, 2pi/3, 4pi/3, and 5pi/3. I'm going to end this video with this example. I have one more complicated example where you will wind up with 8 answers. I will cover that in the next video.